Okay, so now we want to recognize multiplicities of roots from a graph. So let's take again a cubic polynomial f of x, ax cubed plus bx squared plus cx plus d, and these coefficients are real. So how do you graph a cubic polynomial? Well, what we know from calculus, and just for simplicity, in fact, let me assume that a is greater than 0. So a cannot be 0 because otherwise that wouldn't be a cubic polynomial, but a could be positive or negative. So just for this picture here that I'm going to draw, let's assume that a is actually positive. So then I know that as x goes to infinity, then this value of this polynomial also goes to infinity. So I know there's going to be like a piece of this graph somewhere here. And similarly, when x goes to negative infinity, well, if you cube negative numbers, you get negative numbers. And that term dominates the other ones as x becomes large in absolute value, then that means this term will be negative and much larger in absolute value than the rest. So when x goes to negative infinity, then I also know that the value of the function will go to negative infinity. The third thing that I know about polynomials with real coefficients is that they are continuous functions. So by the intermediate value theorem, because here I have it below the x-axis, and here I have it above the x-axis, right? This is the x-axis, it's the y-axis. It must intersect the x-axis somewhere. So I already know, therefore, that it must have one real root. See, without really any algebra, just by calculus, I know that a cubic polynomial with real coefficients must have at least one real root. It is also true if when a is negative, right? Because then it's just this bit comes here and that bit comes there, still on the opposite sides of the x-axis, so it has to intersect the x-axis somewhere. So even from calculus, I know that every cubic polynomial has at least one real root. But by the proposition we proved in the previous video, I know that if it has two real roots with multiplicity, it also has a third real root. So suppose it has three real roots with multiplicity 1. So that means I can write this f of x as x minus alpha, x minus beta, x minus gamma. These alpha, beta, and gamma are real. And suppose each have multiplicity 1. So that means these are actually three real roots. So then if I look at this polynomial, if I look at this factorization, right, I can sort of draw here my, actually I'm going to mark them here. So they each have multiplicity 1, so they're different. So I'm going to assume that alpha is less than, beta is less than gamma. Right, I'm just going to write WLOG, which means without loss of generality. Okay, so these are three different roots, three different real roots. So one of them has to be the smallest, one of them has to be the middle one, and one of them has to be the greatest one. So I'm just going to call alpha the smallest one and gamma the biggest one. Okay, so that's what it is. Okay, so somewhere here, they are somewhere on the x-axis, so there will be maybe alpha. How about beta here? And gamma here. All right, so three distinct roots. So what happens now when I look at the sign of this polynomial? All right, so first I take a number that is to the left of alpha, so something less than alpha, and I look at this factorization. Okay, so if I have, I'm going to rewrite this factorization here again, so you can just sort of analyze it separately. X minus alpha, x minus beta, x minus gamma. There's a is always positive, right? That's what we assume. So if I take, so case 1, cases, x is less than alpha, then what do I have? Well, a is always positive. X minus alpha, if I take x less than alpha, then x minus alpha will be negative. So that is negative. What about x minus beta? Well, x is to the left of alpha, so of course it's less than beta. So x minus beta is also negative. And again, x to the left of alpha minus gamma, that's even more negative. So I have three negatives, so altogether I get a negative sign. As expected, this graph starts here, right below the x-axis. What if I'm in between? So x greater than alpha but less than beta. Positive. Oh, x is greater than alpha, so x minus alpha is going to be positive. But it's less than beta, so x minus beta is going to be negative. And it's also less than gamma, so x minus gamma is also negative. I have an even number of negative signs, so I get a positive sign. So that means this graph goes up here and it intersects the x-axis and goes towards positive. Becomes positive. Okay, so let's take now x between beta and gamma. A is always positive. X minus alpha, well, x is now bigger than beta even, so x is somewhere here. So that means x minus alpha is going to be positive, and x minus beta is going to be positive, but x minus gamma is going to be negative because x is less than gamma, so I get a negative sign. Also, that means that once this graph gets to beta, it actually goes back to the negative side. And I mean, you already know what's going to happen, right? If I take x greater than gamma, I get all the positive signs. So the graph becomes positive again. So, almost was able to connect it with my initial. So that's the graph of a function, of a cubic function that has three real roots, right? You see three intersections here. What you can see is that the tangent lines to the graph at each of these roots are actually not horizontal. Okay, I mean, why do I care about that? Because in a moment I'm going to do a case where you have a multiplicity 2 root. So what happens is that the graph goes through a root and then the function changes sign. Every time changes sign every time as it goes through a root. Okay, so now let's make another assumption. Let's now suppose that, so now case 2, alpha has multiplicity 2 and gamma has multiplicity 1. So in other words, alpha is equal to beta. Okay, what happens then? Let's go back to our table. So instead of writing x minus alpha, x minus beta, I'm just going to write x minus alpha squared x minus gamma. Right, what happens here? Now if x is less than alpha, a is positive, but this term is always positive now. Right, let's just erase these other cases here for the moment. That term is always positive regardless of what x is because it's squared, so it's always positive. 3 terms now. What about x minus gamma? Well, x is less than alpha at the moment, so here I'm going to make an assumption that alpha is less than gamma, again without loss of generality. One of them is smaller, one of them is bigger. I'm going to take alpha to be the smaller one. Actually, I'm not entirely correct here saying that I can do it without loss of generality, because now there is a difference between these roots, right? Alpha has multiplicity 2 and gamma has multiplicity 1. So now I'm sort of forcing the one that has multiplicity 2 to be the smaller one, and the one that has multiplicity 1 to be the larger one. But in fact, I'll leave the other case to you. When alpha is bigger than gamma, you can try to do this and see what happens then. Exactly the same thing actually happens in terms of signs. Okay, so I'm assuming alpha is less than gamma, A is positive, this is always positive, so it's only this term that can, this factor that can change. If X is less than alpha, then it's less than gamma. So this is negative. Okay, so I get a negative here. Then I can have X between alpha and gamma. Positive, positive, without thinking, they're both definitely positive. What about X minus gamma? Well, X is still less than gamma, so it's still negative. And last case, X greater than gamma, everything becomes positive. Okay, so that's not the correct graph anymore then. So let's correct that graph. So first of all, I have only two real roots now. There's alpha, and there's gamma. Alpha is a root, so that means the graph has to go up to the root. Make my graph look a little better. Okay, so it goes up, still doesn't look very good. Goes up to the root, touches it there, but then, so this is negative, right? Negative and positive. But then as it passes through alpha, it still becomes negative, it's still negative. So it just goes back like this. Stays negative here, and then as it goes to gamma, it goes up because it now goes to positive, right? To the left of alpha, we're negative, below the x-axis. Between alpha and gamma, we are negative, below the x-axis. And to the right of gamma, we're positive, to the right of the x-axis. So what happens here? Because the graph only touches the x-axis, here at the point alpha, the graph has a local maximum here. So f has local maximum at alpha. But what we know about polynomials is that they are differentiable functions. So they have all the derivatives, which means having a local maximum means it's a critical point. So, in fact, this implies that the tangent, so the graph of f is tangent to the x-axis at alpha. Okay? You see it's not tangent at gamma. Okay, I'm not proving that it's I'm not proving here that it's not tangent at gamma, but one can compute the derivative at gamma. Let's do that. Let's actually compute the derivative at gamma to show that it's not. I mean, from the picture it looks like it's not, right? But one should never entirely believe the pictures. I mean, how do I know that it doesn't look like this? Because you might just be thinking that I'm crazy here and I'm trying to prove something that is obvious. But how do I know it doesn't look like this? Alright, here, this will be an inflection point where the tangent line is actually still the x-axis, but then the graph actually intersects it, right? At an inflection point, the graph intersects its tangent line. How do I know it's not that? How do you check if something is a critical point? Well, you can just compute the derivative. So I'm going to do it like this. So I'm taking my f of x to be a x minus alpha squared x minus gamma. Right? That's my function. So I'm going to compute its derivative by using the product rule. So this is my first term, and this is my first factor, this is my second factor. So the derivative of the first is 2a x minus alpha times the second, times the derivative of the inner function is just 1, times the second factor, plus the first factor unchanged, times the derivative of the second factor, but that's 1. Okay, let's do this again together. The derivative, so it's a product of this function and that function. The derivative of this function is 2a x minus alpha times the second function plus the first function, times the derivative of x minus gamma, which is 1. All right, so the question is this 0 at gamma? What's f prime of gamma? Well, that's 2a gamma minus alpha. I'm plugging in gamma for x. Gamma minus gamma plus a gamma minus alpha squared. What do I notice? Well, this is 0. So that entire term is 0. But this is not 0. Because my alpha is not equal to gamma. So this is not 0. So I have a 0 plus non-zero. So this is not 0. Okay? And the same calculation can be done to this other case when we had 3 distinct roots. You could see that the derivative is not 0 at any of the distinct roots. However, now that alpha was a repeated root, we actually got a tangent line. But it's a tangent line where the graph does not intersect. So the x-axis is the tangent line, but the graph does not intersect the tangent line. It stays on the same side of the tangent line. So alpha is not an inflection point. The last case that we have is the case where we have multiplicity 3. But that's actually easy. So case 3, alpha has multiplicity 3. Because then f of x is just a x minus alpha cubed. All right, and something that you know from like high school, I think it's high school. How do I get the graph of that? I can start with the graph of that, and then I shift it right by alpha. So, what do I get? If I just look at the graph of ax cubed, it looks like this. And I'm kind of interested what happens at that point, right? This graph has only one root, namely 0. I just want to note the derivative here, just to be sure what happens to the derivatives. So f prime of x, that's 3ax squared, so f prime of 0 is 0. So this is a critical point. So x-axis is tangent to the graph of f. Actually, it's not f. I shouldn't call it f, right? Let's call this g. My f is this, so let's call this g. Is tangent to the graph of g at 0. But it's tangent in a different way, right? You see that the graph actually crosses the tangent line. It crosses to the other side of the tangent line. It's an inflection point. So what about the graph of this, of f of x? Well, let's just shift, right? So, I don't really know how to shift. It looks terrible. Okay, and this is alpha. So same, this is a tangent line. The x-axis is the tangent line, but it actually intersects the graph. So let's write down a summary here of these 3 cases. So, a little summary. So it's the same f. F has 3 distinct roots, distinct real roots. Then that leads to a graph like this. So in words, x-axis not tangent, never tangent to the graph. Never tangent to the graph of f. Again, I encourage you to compute the derivative using the product rule like I did for the other one, and you will see that it's not 0. So f has one root alpha with multiplicity. It is a real root, yeah, one real root. Alpha with multiplicity 2. And one real root. Gamma with multiplicity 1. So what do you get then? You get this. This is the alpha, and this is gamma. So the x-axis tangent to the graph of f at alpha but the graph does not intersect the tangent. At alpha. Okay, and finally, f has one real root with multiplicity 3. Alpha with multiplicity 3. Then the graph looks like this. There's alpha, x-axis, tangent to the graph of f. At alpha, and this tangent crosses the graph. At alpha. Okay, maybe I shouldn't say doesn't intersect, doesn't cross the graph. Okay, these three situations can happen for a cubic with real coefficients and 3 real roots. But we want to study that situation, not that situation. So how far are we from this? Actually, not very far. This looks kind of special, but not as special as it might seem. In particular, it's still what can happen when a cubic crosses a line, but this line is the x-axis in every time, right? It can cross like in 3 different points. It can cross in 2 different points. It can cross in 1 point, and then counting these multiplicities, we see that in fact it sort of always crosses it 3 times, provided that we know that 2 of the roots are already real. Then it always crosses it 3 times, but like this, or like that, or like that. Okay, let's now get to the situation that we want to study, and in fact I'm going to right away give you an example of a cubic that is an elliptic curve. So consider, so it's an orange curve, so consider a curve given by an equation of the form. It's kind of a strange looking equation, okay? All right, something like this. In fact, I'm going to insist that we assume the curve is smooth. If you do if you look at a curve like this, you get more or less a graph like that. You'll see in the various links that I give you in the Google Classroom how by modifying these A, B, and C you can get different shapes of this graph. So a few comments here. First of all, I don't seem to have a coefficient in front of x cubed. Right, we're not going to bother with that. Secondly, I do seem to have an y squared instead of y. Yes. All right, so a general cubic curve can even have other powers of y here and can have mixed terms. That is something like xy or x squared y in it. It turns out that every curve that can be written in such a complicated way can also be written in this way. It would change its graph somewhat, but not in a way that is meaningful to the theory. So without loss of generality, we can assume that all the curves we want to study, the so-called elliptic curves, actually have an equation of that form. Okay? We're not going to get in deeper into this. There's some theory behind it that would be sort of way beyond this course. What we just sort of say is like, we're going to study these sort of curves. They're actually very interesting, just these curves, without having to complicate it any further. The coefficients will be real, and what do I mean by smoothness? Well, essentially that means that this thing has partial derivatives. So it doesn't have any sharp corners. Okay? So in the next part, we'll see what happens when we cross that with a line.